Hi, it's Daniel. You'll have to excuse my voice in this episode. It was a bit raspy, but much more importantly, today's guest is somebody whose work I've admired for a long, long time. The way he describes his current research interests are as including applications of machine learning to computational physics and connections between differential geometry and unsupervised learning. This is manifested in a really fascinating body of work on topics like ab initio quantum chemistry with neural network wave functions and disentangled representations in manifold learning. I have to say, in a time like this, it was very refreshing to have a conversation where the word AGI didn't come up too much. I hope you'll enjoy the conversation and learning about David's work. But now, David Pfau. Before I start asking you a bunch of questions about your papers, actually, I noticed something that was a little bit funny. So, as one does before an interview, I went and Googled your name, as you would want to do when doing research about somebody, and it was very funny to me, totally unconnected to the whole AI summaries thing. That Google, when it gives that kind of summary of who David Pfau is under your name instead of researcher, it says critic, and I don't know if you're already aware of that, but I thought it was really funny, and I'm like
No,
wondering,
I hadn't seen
yeah,
that. Good to know that that's what Google thinks my legacy is.
yeah. How do you feel about that?
How do I feel about that? Well, I have noticed recently, some machine learning conferences I go to, people will come up to me and say, "Oh, I love your Twitter," and my usual reaction is, "This is great, but have you read my papers?" So I hope that I'm more known for my science than my hot takes, but at least I'm known for something.
Well, I hope we'll get most of the time to talk about your science today. Then, so I kind of wanted to start with a series of papers that I think are really motivated by what can machine learning do for the sciences, and I suppose that's an interesting broad thing because at once I feel like I see two strands of thought among people who are thinking about how this can be used. Where on the one hand, I feel like this is maybe the domain of people who are thinking about autonomous agents or something where they have this vision of how can I build a system that is going to enable scientific research in terms of this scientist that will do the research itself. And then on the other hand, you've got a lot of these methods where you're thinking about what are existing methods that we use for things like quantum Monte Carlo, and then where do neural networks plug into that? And that's very much where your research is fitting in. But I'm wondering a little bit about how you began thinking about this was a thing I might be interested in and want to do, and like how you got motivated to think about those problems.
Sure. Well, I'd say I've been focusing more on kind of scientific applications of deep learning, I guess I would say, maybe since around 2018 or so. Maybe some of the ideas were kind of in the air even further back than that. But I should say my background really, I'm not a computer scientist by training. I was physics undergrad and did my PhD in computational neuroscience. And so, my PhD was on machine learning for neuroscience and, analyzing neuroscience data. I think at the time, AI was still sort of a dirty word, and to be as serious as possible, you called it statistics for neuroscience, just to make sure it didn't sound too exciting. Um, but but maybe coming from that, I'd always had one foot in the world of more like laboratory science or scientific applications. So it's always been an interest. At the same time, part of what drew me to machine learning was less as a tool um, for just analyzing data, but as sort of a model for how the brain works or how cognition might happen. So what now we'd call more AI. Um, And so as I did more of that, I sort of drifted more into an interest in sort of pure machine learning and less applications for neuroscience. I wanted to, use neuroscience or use machine learning as a model for how the brain worked, not as a tool for analyzing the brain. If that distinction makes sense, less as sort of a way that you might come in and take a data set from an experimental lab and crunch the numbers, but more as it might be like a model system to do things that the brain does.
I'm wondering about how seriously you take some of those analogies, especially given your neuroscience background, because I do feel like there's a little bit of the people will notice here are things in neural networks that correspond to the ways we've found the brain to respond to certain inputs in the world. And then, of course, I think people have become a little bit looser with going in the other direction as well and supposing that maybe using the ways that LLMs behave, for instance, to inform how they think about how humans behave and all of that. So I'm wondering what that looked like for you.
That's also a very good question. I guess I've always thought that the way that neuroscience has developed, at the time that I was doing it, everybody was fitting like generalized linear models, so basically like a one-layer neural network to neural data. And when deep learning became kind of legitimized in academic circles, people then started fitting neural networks to, deep neural networks to the brain. And when it was convnets, they fit very well. And, now that sort of vision transformers have run away with things, I think they fit, maybe slightly less well. But in many ways, vision transformers work better in many ways. So I always felt that, deep learning has done very impressive things for sort of building things that do brain-like things, but as a tool for understanding how the brain works, it feels like it's kind of going in the wrong direction, because what you want from a theory is something that has as few free parameters as possible. And a deep neural network, as you're trying to make these things as big as possible. So it can fit the data better, certainly, but you lose something in terms of explanatory power. You might say, okay, we don't understand how the brain works, so let's fit a neural network to it. Now we don't understand how the neural network works. Of course, what you can then do is you can, maybe take the neural network and start doing experiments on that you wish you could do on a real brain and can't do that. And there are many people who've done that quite successfully. But at a certain point, I kind of moved in a different direction in my own career, and kind of still check in on colleagues in neuroscience every now and then, but don't really consider myself a neuroscientist anymore. But you were asking about how I see sort of AI for science more broadly and how that fits in. So the time that I started kind of looking at some of this stuff, like some of this work on solving the Schrodinger equation with deep neural networks, the idea of building a sort of AI assistant for science was still kind of science fiction. LLMs hadn't taken over the world yet. It was still even just a few years ago, if you'd said some of the stuff that people are doing now of, hey, take this data and make a figure for me, and it just spits out performant matplotlib code and stuff like that, that would have been seen as impossible at the time I started on this. So certainly, I think there's promising stuff in both directions. I've kind of, I feel like I've made so much headway in what I've been doing myself in sort of using neural networks as tools to do computational physics more accurately, um, that it would be, I don't want to just abandon that. As impressive as LLM work is, I sort of feel like there's still lots of juice to be squeezed out of what we're the approach that we're doing at the moment. I don't think I'm going to, go to an LLM and type in, what's the energy of, here are these molecular coordinates, give me the energy, and it'll spit out the right answer anytime soon. Although there was an interesting preprint from some colleagues, I think former Google Brain people at Google DeepMind, who were showing that with the right kind of prompting and things like that, you can actually get a large language model to kind of do a Hartree-Fock calculation. It's like a mean field calculation. Walk it through the steps, and it can, if you step in to correct it at the right points and things like this, you can get it to do the sort of thing that would be like a graduate physics student would do as a pencil and paper calculation. So maybe the stuff is getting better. You never, every month it seems like something new comes out like this.
I will want to circle back to how you think about some of the directions you're going in a little bit more broadly later. But you said something earlier that also really interested me, which had to do with the ways in which you feel like, I guess, modern ML systems don't really give us a good theory of how the brain works, and this has to do with the free parameters. And I guess I detect something with what you've said that's analogous to kind of parsimony and the types of theories people want. I'm wondering if you feel like you have a sense of maybe a positive picture of the sort of theory that you would want to see when it comes to analogies between this and brains and things like that.
Yeah. Like what would a good theory of what the brain does even look like?
Yeah.
Yeah, I mean, maybe part of the reason I drifted away from this was maybe that I couldn't answer that. It's a very challenging question. I sort of, again, maybe this is why Google calls me a critic, is I can sort of recognize that something's missing, but it's harder to articulate a positive vision of what it would look like. Um, I mean, I can give some examples of what I think are maybe some of the best examples of sort of theoretical neuroscience, at least from the time that I was still following the field closely. Um, I wish I could remember the names of the authors better, but there was a whole series of papers um, where this group, I believe they were in Germany, was looking at the statistics of what are called pinwheels in the visual cortex, and these are so cells in the visual cortex. You have what are called simple and complex cells. Simple cells basically respond to kind of oriented bars in a kind of phase dependent fashion, and then complex cells respond in a phase independent fashion. So it doesn't matter which side's dark or light. Um, and you can map out the entire visual cortex, and at least once you get up to sort of what you might call higher animals with forward facing eyes, things like cats and ferrets and things like this, it actually has this topological organization where you can plot it out almost like a vector field, and you see that nearby cells um, will respond to the same orientation, and then it'll sort of change as you move around. And there are these singularities, these points where all the different cells responding at all different angles meet. And they're actually true singularities down to like the cellular level. So there will be like, adjacent cells that have wildly different response properties. Um, and you look at how widely these are distributed, and you grind through some math, and you look at the ratio of pinwheels um, according to certain parameters, and the number pi pops out. I mean, to the precision that they can measure it experimentally. Obviously, not to more than a few significant digits, but pi comes out for some reason. And they have this very beautiful theory showing that if there's some balance of excitation and inhibition, and it happens on different times on different length scales, then you would actually expect exactly these statistics to happen. So it has both sort of this level of mathematical precision, and also there's sort of a simple but universal mechanism that it implies. So that I think is, at least during the span of my PhD, that was probably the most beautiful and kind of elegant theoretical work I saw. And they tested this across many different species and saw that this held up for, again, any mice don't have pinwheels, but for any animal with a sophisticated enough visual system that they do have pinwheels, this seems to be universal. So stuff like that, and that's of course a very high bar. Most of biology is messy. Stuff like this is sort of few and far between, but that's the gold standard, I would say, for this kind of theoretical insight. Um, so it doesn't even, seeing this phenomena doesn't even have that many free parameters. As you say, you don't have to fine tune things to get this kind of behavior. So that I always thought was a really beautiful piece of work.
I want to ask you about spectral methods, but maybe before that, I guess it's interesting to note when I talk to different people about what they value in theories, maybe as a super broad question, especially when I'm talking to my friends who are physicists, I feel like they talk about theories and the desirability of theories in a way very similar to the way that you just discussed it, and that they are looking for parsimony and kind of a mathematical beauty in a sense. And I'm wondering if you were to reflect on what you take to be the desirable features of a theory, if you feel like that physics and neuroscience background has kind of influenced you in a way that maybe compared to other people you meet who also think about what they want out of theories? Have you encountered people who you feel like have a totally different set of criteria for what they constitute to be a desirable theory, or do you feel like your criteria feel like relatively universal?
Well, I think anybody who thinks the way I do would call it universal, but
Yeah.
but I'm can step outside of that enough to say that that's probably not true. Yeah, I mean, I've um, even though I don't really consider myself a physicist anymore, I guess I consider myself more a computer scientist playing in physicists' backyards. I suppose that kind of culture, I don't know, it's like the way I was raised. It's like even if I'm not a practicing physicist anymore, I'm still it's like the religion you were brought up in almost. But yeah, it definitely was a culture shock, kind of first coming to neuroscience and then to machine learning and understanding the different desiderata that each field has for what's considered success. In neuroscience, if you're an experimental biologist, you care quite a lot about mechanism, and you want to say, what is the biochemical pathway, or what is the cell type, or what is the circuit that's causing this behavior, and you want to tease that apart and do sort of, what are the necessary and sufficient conditions for this. But you don't necessarily care about that universality or parsimony. It's more about, decomposing a circuit and finding that in machine learning, and especially AI. It's more about, machine learning. It's just okay. Number goes up on the test set in a lot of cases, but it's also uh, AI is, in some sense, it's more of an engineering discipline than a science, because it's about making things work. It's understanding is only as good as if it helps you build a more performant model, if it helps you build an architecture that trains better or works better. So and in some ways, it's a much more goal directed discipline. It's, you're trying to build something that the world has never seen before, as opposed to, obviously there are people who do sort of science for AI and science for deep learning and science for LLMs and things like this. But in some sense, that's maybe the exception. So yeah, absolutely. There are different cultures, and I think the most interesting stuff comes when you have this clash of cultures, and you have to kind of work out, and each side has to kind of learn the vocabulary of the other, but also the ways of thinking and the ways of working of the other. That's where the really sort of novel and interesting stuff comes out, and this is why I really like working in interdisciplinary stuff in my career, because you do get this surprising stuff coming out, or you approach problems at different angles, or you come from a different background, and so you can see a problem in a very different light from people who might have been working on it for decades already.
Yeah, I think especially the disentangling by subspace diffusion paper that we're going to discuss a little bit later did a lot of that in a really interesting way. But maybe we should start a little bit with the spectral inference networks, and then we can kind of go into some of your other work connecting ML and physics. And I guess in this paper, you were kind of looking at why a lot of ML methods had transitioned or translated to the deep learning era, but like spectral learning didn't seem to be doing the same thing. And I guess you kind of identified the difficulty of thinking of like spectral decompositions as an optimization problem. And I guess I'm thinking a little bit about, as I kind of went through the sequence of papers that you had and kind of read them back to back to back, I think especially as you were looking at formulations of this type of problem with respect to the Rayleigh quotient, there's a pretty clear connection to some of the stuff that comes up in your later papers on like ab initio solutions and things like this. And I guess I'm wondering if you feel like at the time you were working at this paper on this paper, if well, I guess you were in the paper. There's already kind of connections being made there, but I'm wondering if you have a sense of like to what extent you had been thinking about the stuff that was going to come out in like FermiNet and some of these later papers at the time.
Yeah, I mean, you've correctly identified that there is this sort of thread running through all of these papers, and some of this just comes from, you have the ideas that you fall in love with kind of early in your academic career, and then you find ways to connect them to what's going on at the time. And when I was in grad school, I really fell in love with this paper by Arias, Edelman, and Smith on optimization on matrix manifolds. And basically, it's just one of these papers that unifies all of these ideas in this very elegant way that you didn't even realize before reading it kind of was possible. And it's also just a very thorough kind of review article on all these different kind of disconnected things. And I had studied a lot of optimization in my PhD. So second order methods and convex optimization and semi-definite programming and all this sort of stuff. Of course, that's all in sort of vector spaces. And this paper was about how do you do optimization when the object you're trying to optimize is not a vector, but a subspace or an orthonormal matrix. And then you're not doing optimization in a vector space, but then you're doing it on a curved manifold. And a lot of math works out really beautifully. Like, for instance, you can show that different algorithms for computing eigenvectors, like the power method or inverse iteration, are basically matrix manifold instances of different classic optimization methods, like gradient descent versus Newton's method. So these theorems about, um, the power method might converge linearly while inverse iteration converges cubically. I mean, don't quote me on that, but I think it's something like that. That just falls out as saying, like, okay, gradient descent converges linearly, but Newton's method converges cubically for under certain conditions. And it was just one of those sort of like, mind exploding moments where like all the pieces kind of fall together. Um, and the spectral inference networks paper, this would have been about 5 years later. Uh, there was a lot of work on, um, and also I want to say, so this also ties into some of the ideas that later fed into disentangling by subspace diffusion into Geomancer is the name of the algorithm in that paper. Because also a lot of when I started in machine learning, um, there was still a lot of interest in what you call nonlinear dimensionality reduction. So this was like taking PCA and generalizing it beyond, PCA just gives you a linear projection into a low dimensional subspace. How do you do nonlinear projections into low dimensional subspaces? And so this was things like isomap and LLE, locally linear embedding, row ice and sol, Laplacian eigenmaps, that sort of stuff. And in the time when deep learning was verboten, these were non-parametric ways of doing this. In what now everybody would do it parametrically. Everybody would do it with a deep neural network. So that was also very influential on me, kind of early in my career. So this was all kind of in the back of my mind when I was thinking about this stuff. And so spectral inference networks. That was a time when a lot of what people were doing at DeepMind was, you had a lot of people working on unsupervised learning. That was mostly generative models. So, normalizing flows and VAEs and things like this were and GANs, of course, were the cool thing at the time. Um, and this was all really good for generating images. But there was sort of this sense of, okay, well, how can we use this to do what other people at DeepMind are working on? How can this be helpful for the people trying to get deep reinforcement learning agents to work better? And there, you don't want something that goes from some low dimensional representation to pixels. You want something that goes from pixels to a low dimensional representation, and you don't care about how good it is at generating things. You want a representation that's useful for something downstream. So you just want a mapping from high dimensional spaces down to low dimensional spaces. And I was thinking, like, okay, well, 10 years ago, people in machine learning, 10 years before when I was thinking about this, people would do that with these nonlinear dimensionality reduction techniques. So what was the equivalent of that? And all of these techniques, you basically construct a big gram matrix and diagonalize it. Um, and I actually had already had the idea for Geomancer and was kind of working on that. And somebody said to me, "Oh, can you just do this by gradient descent?" And originally I was just like, oh, that's dumb. Not everything's gradient descent. There's more to life than gradient descent. Then I started thinking about it. I was like, well, wait a sec. How would you do this by gradient descent? Because it's a spectral method. So how would you do a spectral method by gradient descent? Because there are all sorts of things you get out of like just classic PCA that you don't get out of training a VAE or something like that. Because if you compute PCA for k dimensions, you automatically get PCA for k minus 1, k minus 2, down to one dimension for free. You get everything. Whereas if you train, an autoencoder with a k-dimensional subspace, and you want to say, okay, how would this do with different numbers of dimensions? You would have to train them independently. So there's this nice kind of automatic decomposition that happens when you solve an eigendecomposition. And I hadn't really seen that property in a lot of deep learning methods. So I kind of set out to try to do that with spectral inference networks. And it kind of worked, but the optimization was very messy and it didn't converge well if you didn't kind of fine tune the learning rates to do this um, bi-level optimization where, one thing is being optimized towards an objective that depends on some other function that's also changing, and the two problems are coupled together. We've heard GANs have this problem also. Actor critic methods have this problem also. I wrote a whole kind of position paper with Oriol Vignals on connections between them, and the difficulty of doing bi-level optimization. So I was quite happy that we got something that did work if you kind of tune the learning rates right. At about the same time, people started doing contrastive learning, which at the high level is pretty similar. You're not trying to do generation. You're just trying to go from a high dimensional observation down to a low dimensional embedding. And contrastive learning really took off because they didn't worry too much about making it an exact mathematical equivalence with PCA under the right assumptions. They just said, let's do something that works and training is stable. And so, I really liked that it had this connection to eigendecomposition, and it had this connection to slow feature analysis, which is something that, again, coming from my neuroscience background, a lot of theoretical neuroscientists really like slow feature analysis. And there is this formal connection between Laplacian eigenmaps and slow feature analysis. So, in some sense, I was saying, okay, spectral inference networks is kind of slow feature analysis done right. It's using all the modern tricks of deep learning, and in fact generalizing it beyond that to operators other than just Laplacians. Um, so I liked it kind of for the pure math, but in terms of doing practical large scale machine learning, people pretty much ran away with contrastive learning. So this is time and time again. I think I found that I really like things um, that have very nice mathematical properties and have a sort of nice story connecting it to other branches of math and other kind of areas like that. I like connecting all these ideas together. Um, Maybe this is my own instance of the bitter lesson is that oftentimes the stuff that does really take off is just the stuff that scales and works well and is stable to train and stuff like that. But yeah, sort of following on from this work on spectral inference networks, again, just from like undergrad math, it was sort of, or sorry, undergrad physics, just remembered like, oh yeah, hydrogen atom. I sort of vaguely remember that one from like my junior year of college. Let's add that. Let's put that in the paper as a baseline, just to because you can solve it in closed form. So this is a strong guarantee that we're doing the mathematically correct thing. I wasn't really thinking at the time about having it as a practical tool for computational quantum physics. But when we did do that, there was also a lot of interest in uh, not just from myself, but broadly across DeepMind. A lot of people were starting to think about what kind of scientific applications can we use these things for. AlphaFold was just getting off the ground. There was also a lot of interest in density functional theory. So we had a science paper out on that about 3 years ago. This is where you're trying to, rather than just directly solve, so the Schrodinger equation describes how like electrons, for, well, really any quantum particles work. But to solve that means solving for the behavior of all electrons simultaneously. Whereas in density functional theory, you just care about sort of the marginal distribution of electrons. And there's some very nice theory showing that if you knew what's called the exchange correlation functional, then you could get the exact energy of the system. So you don't actually need to know the joint probability of all the different electrons, just the marginal distribution, but you don't actually know what this exchange correlation functional is. So we were using deep learning to learn a more accurate exchange correlation functional. And this project was also just getting off the ground, and I was talking to people about this, and sort of saying like, well, where do you get the data from? And they're like, well, we'll use coupled cluster, which is typically kind of considered the gold standard for if you want to compute the full joint probability distribution over electrons. And I said, oh, well, is that really accurate? And they were like, oh no, this has all sorts of issues too. It's like, well, if you're using that to generate your data, it seems like you might want to solve that problem too. And I said, well, neural networks are great at approximating high dimensional functions. Wave functions are just high dimensional functions. So let's use a neural network to approximate a wave function. And again, I wasn't the first person to think of this. There was a science paper from Giuseppe Carleo about a year before where they had done this on just like a simple lattice model. But if you want to do it for like real like chemistry or materials, you need to solve for particles in continuous space where an electron can be anywhere in 3 dimensions. So it's a much more challenging problem, and there are certain symmetry constraints, or rather anti-symmetry constraints. So it's a much more challenging problem. So originally, I tried doing this with spectral inference networks, and it was noisy and difficult to get it to converge, and just sort of slow. But then the math works out very nicely in computational physics, especially these ab initio calculations. So they're from first principles. You're not actually training things on data. Sometimes people look at this and they say, okay, well, it's not supervised, so it must be unsupervised. It actually goes further than that. It's like undataized. It's you're generating your own data. You're really just trying to solve an equation, and you can just write that down on pencil and paper what that equation is you're trying to solve. I've sometimes called it self-generative learning because the network generates its own data. So feel free to use that one. Um, so as I was saying, where was I going with this? So because you can sample from any distribution you want to, you're not just given data from some distribution that you can't control. You can actually get around this issue that I said of with the spectral inference network of having this messy, unstable bi-level optimization. And you can actually get out unbiased. You can formulate things in a way where if you sample from the correct distribution, you get unbiased gradients. And then just everything becomes gravy. Like everything's easy. Your learning curves just converge very quickly. Optimization is very stable in comparison. And so sort of once I saw that, I said, great. I'm like all in on solving these physics problems because it just started working really well. And that was 6 years ago now, and kind of haven't looked back.
Yeah, there's I feel like there's a lot of interesting takeaways in these series of papers, maybe starting with the spectral inference networks, actually. One thing I noticed in the deep slow feature analysis one was it was kind of interesting in the example you used where you trained the CNN to extract features from videos. And I think the example you used was something like 3 bouncing balls. And you found that the eigenfunctions encoded these super interesting things where like when you plotted frames that most positively or negatively impacted one of the features you saw, it encoded like whether all the balls were crowded in one of the corners or one of the balls was in that corner while the other two balls were away from that corner. And it was this kind of interesting nonlinear feature. And you kind of were positing that higher eigenfunctions could encode for like even more complex relationships. And I'm wondering if that's like something you explored, and maybe how you think about your intuitions on some of that.
Yeah, no, there was definitely a really interesting kind of interpretability angle from that. Yeah, unfortunately, there's only so many hours in the day and only so much you can do in one lifetime. And I would have loved to have followed up on that more, and would have loved if some other people had followed up on that as well. Um, so we tried to get some people interested in this. I think some of the issues around stability and training maybe made it difficult to scale it up a bit. But you know, in theory, I don't see any reason that even today somebody couldn't pick that up and run with it. It does get difficult to kind of that was a simple enough problem that the features that came out were relatively interpretable. Um, Interpretability, of course, is one of these questions like you asked earlier. What makes a good theory? What makes an interpretable feature? It is somewhat a matter of taste. Um, I would love to see kind of better tools for interpretability. Of course, now in the world of interpretability, seems like mechanistic interpretability is where a lot of the excitement is, and of course, LLM interpretability is where a lot of the excitement is. So maybe someone listening to this will be inspired to try to use spectral inference networks for mechanistic interpretability. I know they like sparse autoencoders quite a lot, and even seeing some of the dictionary learning stuff that has been picked up on there again brings me back to my neuroscience days. I know a lot of people in that field also are sort of also come from a bit of a computational neuroscience background. So it does feel like a lot of people get to do the neuroscience they always wish they could do, and now they can because they have perfect knowledge in kind of artificial brains, if you want to call them that. Which I usually wouldn't call them that, but some people might call them that. But yeah, no, we didn't follow up on that as much as we would have. I think because the people in Vision mostly, as I said, picked up and ran with contrastive learning. And I do think one of the beautiful things about spectral inference networks was that it gives you this natural ordering of features. Um, so it does sort of force things into, for lack of a better word, disentangled directions along sort of each of these directions. And I'd hoped that people would pick up on that more. Some of this may have just been a question of timing, I think, because I think when we published that, it was just kind of at the when I think research on disentangling was maybe at a high watermark. This stuff always is kind of cyclical. The pendulum always swings back and forth. I think maybe 2017, 2018 was when disentangling was maybe at its trendiest. Um, and yeah, I for whatever reason, I don't know quite why people didn't look at it more. I think it's the sort of thing that often you can't just put out one paper and expect other people to say like, awesome, let's do it. You really do have to sit down and work with people and um, make the case, and can often take a series of papers before people really see the unique benefits of a particular method. But I still think there's opportunity there to take this idea of a kind of natural ordering of states and a natural ordering of dimensions to get more interpretable features. That was, I think, part of the hope of the beta VAE, which at the time was, or TCVAE, or any of these methods at the time. Possibly because these methods already existed, they might have said like, okay, maybe it's just another one in a list of things that it's hard to see why it stood out. But yeah, I don't really know why.
Yeah, I guess there's sort of an element of maybe self advocacy, and part of that kind of has to do with following up on your own work that feels important and getting attention on these things. And maybe that also just has to do with, I don't know, I guess to what you said, maybe there's a timing thing, maybe there's the only so many hours in a day and there's other things you wanted to attend to kind of thing. Yeah, I don't know. That's interesting. I'm wondering if maybe somebody will turn a bunch of attention to this at some point, and then things change completely. But
Yeah, I think so. I mean, it does seem like, also today, with kind of transformers having taken over everything, including vision, um, it seems like these contrastive encoders, I mean, like clip, of course, that's a contrastive encoder. And so you do get kind of obviously useful features out of that, and features that kind of co-align with natural language quite well. Um, and so it seems like the drive in the last several years, I guess spin was what, 6 years ago now, which is a little terrifying. It's been towards higher and higher dimensions and more complex representations, and foundation models that can do everything. And this, in some sense, was from an era of more narrow, train on one data set, analyze what it does there. ImageNet was big back then, and now even ImageNet seems like a tiny data set in comparison. So maybe these ideas will have their heyday again, because obviously there is quite a lot of demand for interpretability. Um, I think from my own point of view, as I said, only so many hours in the day. So I put a lot of my time into these quantum applications, but I also always saw spin as a stepping stone towards Geomancer. So I put more of my time and focus towards that, and that was really about not just kind of taking something that already existed and deep learningifying it, but really trying to do something that I hadn't seen anybody do in machine learning before, and try to come up with almost kind of a new learning paradigm, I guess, like learning from curvature, using using information about curvature and image manifolds as a meaningful learning signal. I've never seen anybody do that before, and that was what really excited me about this and what really got me into this. And maybe to the detriment of my own impact, I didn't put in the time that I should have to just showing that what I'd already done was practical and useful. I was sort of chasing the grand idea. But in terms of the trade-offs you have to make in a career, I'm happy with having chased the big ideas. So
The grand idea thing is really interesting. I want to get to that, but I do have a last question on spectral inference networks, which was I pulled something, a quotation from the paper that had to do with the optimization problem. And it sounded like you or whoever wrote that sentence was kind of surprised at something. And this had to do with finding the lowest eigenvector of a matrix by minimizing the Rayleigh quotient. And it said, amazingly, which was the key word in that sentence for me, despite being a non convex problem, algorithms such as power iteration, which you mentioned earlier, converge to the global solution of this problem. And given that this sentence started with amazingly, I'm wondering if you have intuitions on what's up there.
yeah, I mean, you can write on a whiteboard pretty easily a proof that power iteration will converge. It's just if you decompose your vector at each step as a sum of eigenvalues, the coefficient in front of each one will get multiplied by the eigenvalue, and as the name suggests, after n iterations, the coefficient in front of each one will be multiplied by lambda to the nth power. So it's sort of obvious that one will blow up and dominate over all of the others. Um, Maybe it's amazing to me because, as I said, quite a lot of my background and my PhD was in convex optimization. And there, the Raleigh quotient is like, okay, it's quadratically constrained, or the constraint surface is a quadratic surface. Um, it's a non-convex set, the set of all the set of all unit length vectors. Um, and so, they just hammer into you in convex optimization, like this only works if your constraints are in a convex set. So it works in a linear space, but not a sphere. Although technically, because positive and negative eigenvalues are, or eigenvalues are only unique up to a sign, it's actually not the sphere. It's actually the projective sphere that you're optimizing over. And so, somebody smarter than me can probably explain why that is sort of equivalent to optimizing over the projective sphere, maybe that actually does look more convex in some sense than the sphere. But I don't understand it. So maybe when I say amazingly, it's because it breaks every intuition that I have about a non-convex optimization. And cases where you can exactly solve a non-convex problem are so few and far between that it does feel sort of faintly miraculous to me. But I think the people who are like professional mathematicians doing convex or doing optimization theory probably understand this far better than a pleb like me.
The projective sphere thing is actually interesting. Maybe I'm jumping ahead here because I was initially gonna take the like projective representation theory stuff as kind of a bridge between the QM things and the disentangling by subspace diffusion, because the Lie group SO3 kind of plays a big role when you're talking about 3D rotations and sort of the Stanford 3 objects data set and things like this, and disentangling. But I was talking to a friend who is an actual physicist about some of this because I wanted to not sound like an idiot when I talk to you eventually. And he was talking to me about how there's this interesting connection between SO3 and then another Lie group, SU2, I think. And that's kind of a different representation. And I guess the thing is like SU2 is a double cover of the projective representation theory of SO3 or something like this. And this also has some implications for the spin of particles, and is why I think if you like do a 2 pi rotation on particles, you don't, it's not like the identity transformation. But I guess what was kind of interesting that he said to me was something like nature sort of behaves in a way that is better described geometrically by projective representation theory, but nobody actually does projective representation theory. So we're doing like the SU2 stuff, but then nature is out there doing the SO3 stuff or something. I'm wondering if that's like a thing that kind of came up as you were exploring these ideas, or that you thought about at all.
I definitely found some stuff when I was working on Geomancer. I think we maybe put it in the appendix that surprised me, but probably says something deep about differential geometry that somebody who knows this stuff deeper than I do would say, "Oh yeah, that's an instance of something like what you just said." So for context, for listeners, what what the thing about Geomancer is every time I've tried to actually give a talk on it, I've never actually found a way to compress it into under 90 minutes. And most academic talks are about 1 hour. So just giving context even for what it is, I can try my best in a short amount of time.
Feel free to
Essentially,
take as much time as you feel you
yeah,
need.
yeah. Thank you. Well, I don't know that we have that listeners would want to stick around for 90 more minutes of this podcast. I'd hope so. Um,
I think some definitely will. So
yeah. um, the basic idea was how do you learn to decompose a manifold from data? If you're given a bunch of instances of data sampled from some nonlinear manifold, and that manifold actually can be described as a product of many manifolds, how can you basically how do you do manifold factorization? Lots of people in machine learning do matrix factorization, but I've never seen anybody do manifold factorization. Um, I think possibly I said it was uh, I called it disentangling in part because that was a cool thing to call it at the time, but maybe I should have called it manifold factorization. But a lot of the examples that we looked at, we started with things that you can describe in closed form, just spheres and rotation groups. But the kind of canonical, the what to me the MNIST of manifold factorization would be was this example in the paper of separating like lighting and rotation for an object in in a fully unsupervised way. So objects are invariant under 3D rotation as well as translation. They're also invariant under different changes in lighting. So this is something that you encounter naturally. Um, in robotics also for 3D hand manipulation, you have to deal with 3D rotation. And 2D rotation is pretty simple. You just go around in a circle. There's only one thing you can do. And you go forward along the circle, you go backwards around the circle. And you bring up physics. So I think SU2 is the fundamental symmetry group of the weak force, I want to say. This is where, as I said, I only got up to undergrad physics. Whereas U1, so basically rotating a complex vector, is the symmetry is the gauge symmetry of the electromagnetic force. So when you go to rotations in 3D, things get much more complicated. They become as a group, that's non-abelian. So the order in which you do different rotations and compose them together matters. And so there's all sorts of complexity there. And I sort of always thought it has to be relevant for vision to some degree because, everything in the world is actually 3D. It might get projected onto a 2D screen or onto, the back of our retinas, but, you're fundamentally describing a 3D world or trying to interpret a 3D world. So you would think getting the details of rotation like that right matter. And coming from a sort of physicsy background to machine learning and learning about things like I said, these things like Laplacian eigenmaps and isomap and stuff like that got called manifold learning. I sort of thought, oh, they must be using some information about the manifold, but they're actually throwing away everything about the manifold. Most of what's called manifold learning is about projecting things from a manifold into a flat space. So it's about getting rid of anything manifold-like about the manifold. So it's almost kind of a misnomer. It's manifold-less learning. It's demanifolding the manifold. And around, I guess, 2013 you had things like word2vec, where you could learn these embeddings of words in a vector space, and you could do vector arithmetic to do analogies between them. So you could take the vector for man and woman, and king and queen, and show that man. Let's see, I'm gonna get the order wrong. So it's king minus man plus woman equals queen, um, and people loved this. It was very influential. That idea has of, I guess, called the parallelogram model of analogy, because these vectors do make a parallelogram, has been around in cognitive science dating back to the 1970s. I think David Rumelhart and others kind of first suggested it as a way that you could kind of mathematically formalize an analogy if you have vector embeddings. But I think until word2vec, nobody had shown it. You could actually make it work with the vector embedding. Um, and again, knowing kind of just enough differential geometry to be dangerous, knowing just enough about manifolds to be dangerous, I sort of said, okay, well, that might work if you have a vector space embedding, but if you go from vectors to manifolds, you can't do that on a manifold anymore, because now the order of operations matters. You can do vector addition locally on a manifold in a tangent space, but it no longer means anything to have a vector from one point on a manifold to another. You can have group operators that map you from one point to another. You can have paths, but things become path dependent on curved surfaces in ways that they aren't in flat vector spaces. And I sort of thought, okay, there's something missing here, because again, people talk about image manifolds all the time, but if we really take image manifolds seriously, then you do have to reckon with things like 3D rotation, which have these, you know, non-commutative properties, these path-dependent properties, and that seems like a huge pain in the ass, basically. So I felt like everybody was trying to skirt around this by projecting things into a low-dimensional space. And I just sort of said, there's got to be some way that we can actually use this, that rather than having it be a bug, it's got to be a feature. There's got to be something you can use it for. And this is an intuition that I'd had for years, but I never figured out how to make it happen, how to actually turn that intuition into a practical algorithm, or even an impractical algorithm. Um, and I finally, one day, went up to Sebastian Racanier, who's a colleague of mine who actually did his PhD in differential geometry. He's a brilliant mathematician. He knows all this stuff like the back of his hand. And I just spent 15 minutes at a whiteboard, sort of saying everything I just said to you, and just being like, there's got to be some way that you can say, okay, if I go in this direction and then this direction versus this direction and that direction, some things won't compare, but the fact that we can make image analogies at all, that the fact that we can reason analogically about images, that suggests that along some dimensions it has to be possible. So there's got to be some way to decompose things. And he just says, oh, you're thinking of the Durham decomposition. And I'm like, I have no idea what that is. And literally just literally just read the Wikipedia page and ask Seb some questions. And it's a very beautiful idea, connecting local properties of manifolds to global properties. And it's basically about sort of necessary and sufficient conditions for for it being possible to decompose a manifold into a product of manifolds. And it uses this property called the holonomy group, the holonomy of a manifold, which is
Mhm.
basically a fancy word for saying if you walk in a big loop, and when you come back around to the place where you started, are you facing in the same direction as when you started or not?
Mhm.
That's basically all that holonomy is. So if you start on the North Pole and you hold out a stick in front of you, and you're constantly holding that stick in front of you, and you walk down to the equator, and then you head east, and so you kind of shuffle with the stick pointing out and you're moving to the side, and then you walk back up to the North Pole, will the stick be pointing in the same direction? It won't. It'll have rotated by some amount, and the amount by which it rotates is the holonomy of that loop, or is the element of the holonomy group. And so the Durham decomposition relates the holonomy group, which is a local property, it's a property around a point, to the different possible um, the the ways that you can decompose a single manifold into a direct product of several manifolds. And the whole idea behind Geomancer is, how can you turn this into something that you can actually compute from data? So if you have a bunch of points sampled from a manifold, like for instance, images of a single object under different lighting and rotation conditions, how can you actually compute whether or not a Durham decomposition exists? And if you wanted to do this exactly, it's a property of all possible loops, and so that becomes computationally intractable, even if you approximate your graph as a manifold. Um, but if you again, and this is where the spectral idea comes in. There are sort of beautiful ideas from spectral theory, spectral graph theory, saying that the Laplacian operator doesn't tell you it doesn't tell you the property of all loops, but it tells you the average property over all random walks. So basically, you say, okay, if you have a particle undergoing a random walk along a manifold or a graph, the Laplace operator tells you how the probability distribution over the position of that particle evolves in time. And so this is integrating over all possible paths that particle can take. So you can see how this would be relevant if the holonomy is a or if the holonomy group is a property of all possible loops that you can make around a manifold, then you can imagine the Laplacian operator would have something to say on average over random walks. So of course, because some random walks are more likely than others, that means some loops are more likely than others. So it doesn't tell you a universal property, it tells you an average property. But computationally, that's generally enough. So then what the Durham decomposition says in more detail is basically that um, if you have a certain starting vector and you go around any loop, if that vector comes from the tangent space of a submanifold, so you can if your manifold is a product of many manifolds, the tangent space at a point, so sort of the locally linear approximation around that point, there will be basically your coordinate system will break down into many subspaces. So we've now gone from submanifolds to subspaces locally. If you have a vector in that subspace, no matter what path you take around, when you get back to the original point, you'll still be in that subspace. It might have rotated, but it will have only rotated within that subspace. So, so then you say, okay, we can turn this into a computational signature for your data manifold being decomposable into a product of submanifolds. So it's not about, so as I said, the Laplacian operator is about, how a particle evolves. This is about how a vector evolves. So if you move a vector around a loop, where does it come back to? But it's not about the vector being invariant, because the vector can still rotate. But the subspace spanned by all of these vectors, the subspace has to be invariant. So if you have a basis for that subspace, when you move it back around, the individual basis elements might have rotated, but the basis will be the same, or the space spanned by the basis will be the same. That is what Geomancer computes. Is it says what are the subspaces that are closest to being invariant, and there might not be any. But there are a lot of nice things that you can do with Geomancer. Again, kind of drawing inspiration just from PCA. One of the nice things about PCA, and again, this is maybe where my neuroscience background is showing, because people love to do PCA on neural data sets and say, okay, there's a drop off after this number of principal components, and that suggests that the intrinsic dynamics of this system are so and so, 3-dimensional, 5-dimensional, whatever. Of course, there's been a lot of work showing that these results often are completely dependent on whatever task you have the animal doing. So what you're measuring might not actually be something intrinsic about the brain, but actually be measuring something about the task. But leaving that aside, certainly all this stuff was very influential on me and shaped my thinking a lot. And that's a really great property for an algorithm to have, that you have this signature of what's the right dimensionality. So Geomancer, in the way that with PCA, you can say, okay, this is the data seems to come from a 5-dimensional subspace because there's the sharp drop in the spectrum of the covariance after 5 components. In Geomancer, you can say, you construct a big second order Laplacian, so a Laplacian that describes the evolution of subspaces rather than particles. And you can look at the spectrum of this giant Laplacian matrix, and that also has a sharp drop, but that doesn't tell you the dimensionality of your space. That tells you the number of submanifolds that there are. So you can actually read out from these results, oh, this is a product of 3 manifolds. So there's a high degree of precision here. There's a lot of useful information. But when I was experimenting with this stuff, I would do this on simple manifolds, and I would get like this is again a long digression, getting back to actually your original question about SU2 and covering projective spaces and stuff like that. I'd see sort of weird results that didn't look like anything that I expected, and would sort of say, "Oh, this is because this manifold has this property that I had never heard of, and what you're actually finding is this other thing." So we had to add in like a few extra constraints that I hadn't originally expected, like to make sure that it only found, basically it would only find projection operators, like operators that would project things onto a subspace. And so these sort of spurious things that it would sometimes find for certain types of submanifolds, probably a mathematician could look at that and say something really interesting about what it was discovering. Um, I'm not a mathematician, so I just play one on TV. So, um, so I don't even understand what was coming out of it. But yeah, there's sort of interesting stuff, interesting follow up stuff there for just. I feel like there's a whole field of computational differential geometry that very few people even look at. Um, and actually, I ended up only finding out later that in developing Geomancer, I sort of ended up reinventing some of what people do in what's called vector diffusion maps. This is there's a whole branch of kind of applied math on diffusion maps, which also was another kind of splinter out of this nonlinear dimensionality reduction field. So guys like Amit Singer or Ronald Kaufman at Yale, people like that. There's a whole academic community around this, and I've always, or at least you know, since I started in machine learning, I've always aimed for the machine learning audience. I've published it, NeurIPS and iClear and things like that. Um, but I do sort of feel like there should be more discussion between these fields because the diffusion maps community. Um, I think at least I haven't bumped into that many of them at machine learning conferences, but it seems like kind of a natural pairing. So I'd love to see more of this stuff get more traction in the diffusion maps community as well because it's sort of a natural connection there. And I only realized after actually was reading some papers from the graph neural networks community because there are a lot of people there who love spectral theory and love Laplacian operators and differential geometry. That apparently the mathematical object that we were constructing in Geomancer, which is basically a graph with uh, a vector space on every node and a linear, basically just a matrix, a linear operator on every edge. So it's basically a discrete approximation to a manifold with a connection. Apparently, this is called a cellular sheaf. I it was only like years after publishing Geomancer that I even heard the term cellular sheaf. But apparently, we were doing cellular sheaves. And the graph neural network community, they use all these tools for designing better neural networks, basically, for designing neural networks that work on graph or manifold structured data. What I was thinking of was with Geomancer was more, what do you do if your data set comes from some structured manifold? How do you discover that structure? But I think there's definitely opportunity for these tools, these analytic tools, to be used for designing, for designing graph neural networks as well. I think it would be very cool to sort of pick these up and find ways that they can be used because a lot of the work on sort of equivariant neural networks and things like that is about building in invariances and equivariances that you care about. And a lot of my hope with Geomancer was to point a path towards how you could go about discovering invariances and equivariances. Because in some sense, if your data is generated by operators that have certain equivariances, that maps out manifolds that have certain structure. So there's a connection there.
There are, I guess, a couple of interesting notes and follow-ups that I pulled out from the paper as well. And there was one part where I guess you noted an assumption you made about data being embedded in a space where the L2 metric and Rn matches the metric on the manifold. And I guess the interesting note was that an embedding like this has to exist for all manifolds, but how to learn that embedding is an open question. And I was wondering if you could comment a little bit more on that.
Well, some of the hope when I started on Geomancer was that you could just take the L2 metric between images in pixel space construct a kind of local subspace around every point on your image manifold that way, and Geomancer would work from that. And we just never got that to work. That just never worked. Part of the reason that I'd waited so long to publish Geomancer, possibly, I mean, we published it at the same NeurIPS that GPT-3 was at, and as I said, 2017, 2018 was maybe kind of the high watermark of at least a wave of research on disentangling. As I said, I think every good idea comes around again, but I really didn't want to publish it until we could get it working from raw pixels. And eventually we just said, okay, look, it works if you have the right metric. We don't know what the right metric is for images. We don't know what the natural metric is for images. Um, that's an interesting open problem in its own right. If you really take, can you design or even learn a correct metric? Most of what gets called metric learning usually is about preserving the metric when you map it from a high dimensional to a low dimensional space. But what if whatever nonlinear transformation generated your data actually radically distorts things? How do you recover the original metric such that that structure becomes clear? That's a really interesting question, and one that is still an open question as far as I'm concerned for images. I sort of think in retrospect, and I think I gave some talks with this title. I probably should have called the paper "The Metric is All You Need for Disentangling."
There was also, I guess, another result you had where you found, especially for more complicated manifolds, there was like a critical point before which your method didn't learn anything. And then after that, it got kind of cleaner estimates with more data. And I guess like intuitively, what I got out of that was something like you need a certain amount of information or amount of data to get a sense of like the geometry of the manifold. But I guess I'm wondering what your intuitions about that were.
Yeah, that's a great question because I'd like to market that as like an unexpected emergent property of Geomancer. Um, but it's a Geomancer is a many-stage algorithm, and I think some people look at it and they get a bit intimidated. But each step is basically just linear algebra. You know, there's nothing in there really that isn't just like nearest neighbors or SVD or something like that. So each individual step is not too bad. But there are a lot of them put together, and we found that the trickiest part was just getting the first step right. And the first step is constructing a nearest neighbors graph of the whole data set. And and I want to say part of the point of the paper was not just to say, hey, we've got an algorithm, but to say, hey, we've got a paradigm, we've got a mathematical formalization of how you could learn structure from curvature, how you could use curvature as a learning signal. And Geomancer is just one possible way of implementing that. Um, and the very first step seemed to be where it broke down the most often. It seemed very brittle if you didn't construct that, because again, if you don't have the right metric, you're going to construct the wrong nearest neighbors graph, and it just won't work. So there could be many different steps in the algorithm where you just don't have enough data to reconstruct something accurately. I think part of the beauty of Geomancer and why I'm still so proud of it is that on simple manifolds, at least, you can learn from a few hundred data points. Uh, so it's extremely data efficient in the simplest case. But again, bitter lesson here. It does scale something like quartically with the dimensionality of the manifold and stuff like that. So that'll bite you at a certain point. So I'm not saying Geomancer is the end all be all. Um, I see it more as a first proof of principle that there is useful learning signal from image manifolds that can be that if you make the right assumptions or you have some kind of signal of closeness, some kind of nearest neighbor signal, you can learn things from that. Um, but as for why there's this kind of critical threshold beyond which it only beyond that where it starts to take off, I don't know. I don't know what the critical step is. It could just be that if you have X% probability of each step failing, you raise that to the fifth power, that's a pretty high probability. And so every one of those probabilities of things failing has to get low before it starts to take off. Uh, that would be my best guess, is that there's some kind of compounding effect from each step in the process.
A last question I had about, I guess, the method and results in the paper. I have other questions about other aspects related to this later, but one thing you noted here and elsewhere was about metric information being sufficient and necessary for disentangling. And I guess as a counterpoint to that, though, you also found that learned embeddings were insufficient. And I think that you were hoping you could use like another embedding representation learning method, and then Geomancer is kind of a post-processing step. So I think you worked with beta VAE, and this didn't seem to work out. And I guess you speculated it's because nothing about VAEs forces them to preserve topology. So earlier this week, when I saw this, I was going to ask you if you tried any like topology preserving methods, and then I had the idea to try to do that myself, and I didn't get as far as like reproducing your code with beta VAE. I was able to run the kind of out of the box initial code. So I did not get very far in my scheme of trying this with like topology autoencoders or something. But I'm wondering if you developed intuitions on that, because I guess like you could ablate that suspicion by figuring out if it does work with topology VAs or something.
Yeah, I'll say the people where I think Geomancer's gotten the best reception is like people who do topological data analysis. So like the TDA crowd like loves Geomancer, um, which I find quite flattering because I don't understand like Betty numbers and like topology and stuff like that at all. So it's great that great that people smarter than me are interested in it. Um, but yeah, no, I haven't really had the chance to try that. And um, yeah, one of I mean, it's just sort of the classic story of a lot of this type of machine learning is it works well when the data is very clean, but it's quite brittle and breaks down easily. And trying to understand the source of that brittleness and ameliorate it is is a quite a big undertaking in its own right. So you know I'm always looking for people who'd be interested in tackling that, and I hope that some people do tackle that. I don't know. I mean, I think even these topological data analysis methods, um, again, they will sort of tell you if you can construct what is it, cyclical complexes, these sort of higher order graphs of your data. It's a way that you can, again, as I said, I'm not a TDA person, so hopefully I'm not butchering this too badly, but that you can sort of construct topological invariants from your data set. But even there, you have to construct the graph or the cyclical complex in the first place. Which so maybe this is of quite a lot of interest to the TDA crowd also, because I think Geomancer, at least our results give you some evidence that for image data, we're not using the right metrics. I mean, we tried rather than just the L2 metric, we tried structural similarity, stuff like that. So some of these hand-designed metrics that correspond to human perceptions a bit better. Yeah, we tried learned embeddings. Since that came out, I think SimClear was probably the thing that really took off in computer vision for contrastive learning, for doing all this data augmentation stuff. So learning good embeddings and good representations using this data augmentation. We haven't looked at using like SimClear features. Maybe that would work. Um, Although the kind of data augmentation they do, it's this persistent question in computer vision. One of the really interesting things I think is that translation in plane, dealing with that is almost trivial. I mean, that's what a ConfNet is good at handling, is they are built to be invariant to in plane translation. But the second you do out of plane or rotation, I guess in plane rotation is a little bit more complicated, but at least translation is easy. But you can at least just like take random pixels. Basically, it doesn't even have to be an image of anything, and you can rotate it in plane. But out of plane, you actually need to know something about the 3D structure of the object. And so SimClear will do all these in plane transformations, but it won't do out of plane transformations. Um, but Despite that, it seems to learn really great features for then doing kind of supervised fine tuning afterwards. But yeah, it does suggest to me that, and again, the world since 2020, so much of things are about learning foundation models, and so you just throw the entire internet at things, and you do learn great features from that. Um, Again, I think maybe this is the physicist in me wanting parsimonious theories and sort of elegant, sort of approximate everything as a sphere. And sure, it's a toy problem, but it gives you insight. That sort of style of things. I still feel like there is stuff to be done on these simple toy data sets where you can fully control all the transformations and actually understand all the transformations behind the data. And maybe for practical computer vision systems, maybe you don't need to hyper analyze like 3D rotation and get the math of that just right. We seem to have gotten pretty far without it so far. But then again, I can't kind of shake the feeling that there's more that we could be doing, or that we could be missing something, and that before you can get something that you just scale up to the entire internet, um, you have to unlock an idea from studying really simple instances first. And those, it may seem like you're just playing around with small things, but I think the deepest ideas come from studying simple stuff, and the ideas that have the most impact are the deepest ones.
I'm wondering if we could talk a little bit about that intuition you have that maybe there's something missing, because I do feel like there's very different perspectives on that, either whether we are missing something at all, and then if we are missing something, what it would look like to figure out what that is. And I guess one way this manifested, maybe going back to something that you've tweeted actually, was like this little table of different techniques that people are thinking about when it comes to scaling. And I think one of the corners had to do with, I think it had to do with like self play, and then having to do with like open and closed situations. And one of the ones that people seem to think is going to scale really far, you were arguing, at least via this table, was kind of impossible or probably wouldn't work. So I'm wondering how you think about maybe the landscape of the what is missing question, like what that means to you.
So, first of all, when I say, I can't kind of shake this feeling that something's missing, I think every good scientist, and maybe bad scientist too, but every good scientist, they almost have to have that feeling, because that's kind of what motivates them. If you sort of thought, okay, everything's been solved, you'd probably say like, all right, my job is done. I'll just retire now. Um, but there's always this almost paranoia that there's got to be something missing, that there's something not quite right yet. And I've even heard, Jeff Hinton, who has spent his entire career being a cheerleader for neural networks since long before it was cool. Even he's said he has this sort of nagging suspicion that there might be, I think he put it, exponential inefficiencies in deep learning. Um, and seeing some of these kind of power law scalings for LLMs and things like that, I sort of have a similar feeling when I see a power law. I don't see like, oh, it'll just keep getting better the bigger you make it. I mean, that's true, but it also means that to get a certain amount of improvement, the amount of extra work and extra compute and extra data you need becomes multiples larger. So sort of the closer you get, every marginal improvement becomes much more expensive. And so you have to wonder if there's a way to get around that. If that's sort of a fundamental, maybe this is something fundamental. Maybe we can't do better than that. But you have to at least wonder, well, what if we could? So that's always the sort of thing that's motivating for anybody who really, who, if you're going to be this obsessive about it and dig this deeply into it, you always have to have at least a little bit of suspicion of like, well, what if we're doing something wrong? What if everything is built on a foundation of sand? You might not have proof of that, but looking for the things, a very, I think, productive research strategy is to kind of hunt for the things where things don't seem quite right, or it does seem like there's a little thread loose. and you just kind of tug on that thread and you just keep going until things fall apart. As for the tweet that you referenced about sort of different strategies for scaling beyond the compute limit, I guess you would say, because there is a lot of that came from basically hearing the same conversation happen over and over again, either in person or on social media. There's kind of this back and forth that goes something like this. Somebody says, oh, deep learning is going to hit a wall soon, scaling is going to hit a wall. They're just running out of data. People have just scraped all the data that there is on the internet, and there's nothing left. In a few years, they're going to run out. And then somebody else says, well, what about, LLMs generating their own data? They say, well, isn't that how like AlphaZero was trained? Like it was all done by self-play. And then, the counter argument to that goes something like, well, AlphaZero was trained on, games, was trained to play chess or Go or Shogi, where you can formally specify the rules. And so self-play works because, even if it learns the rules, there are still a set of rules. And once you know those rules, you can generate an arbitrary amount of data that obey those rules. And in the real world, if you're talking about totally open-ended, train it to do everything that an LLM currently isn't good at, which means fully open-ended. The real world doesn't have rules. It doesn't have rules that you can formally specify like a game. I could see sort of data generation by self-play working in maybe things like formal math, where there are formal rules. Math is in some sense it's the ultimate game. It's a game where like each theorem is its own game. And winning one game can help you win other games, and it's a meta game. But it is still at least formally specifiable. But then, of course, there's all sorts of interesting stuff on can you use LLMs to read math papers or do auto formalization or stuff like that. That's a separate tangent. But as for in the broad scope, what are paths to scaling beyond beyond just scraping the internet? I do feel like things that work for self-play and things that LLMs work for are in some sense incompatible paradigms, and there might be some smaller Venn diagram where that can work, but it's not gonna solve everything. And unless you could somehow come up with some way to formally specify like the whole world, which would be a fascinating research project in its own right, but probably not something we'll solve in the next year. Of course, there might be some way to get things that are good enough that you can bootstrap a bit from that. I have yet to kind of see it, but I've been wrong about lots of things in the past, so I'm not totally counting it out. But I think the part of the point of that tweet was just seeing the same kind of ping pong back and forth of well, oh, we're going to run out of data. Oh, but what about self play? Oh, but then just be like, all right, let's just summarize this all. Okay, now we can move on to actually doing the research and actually seeing if it works or not. But yeah, in terms of what's missing, I mean, there are days where I think everything's still missing. I think we've you know years ago it was solving adversarial problems in vision that was sort of this. It was again one of these sort of threads where it seems like maybe if you pull on it, maybe the whole thing will fall apart. That you have these adversarial examples that are below the threshold of human vision, but completely change the output of a neural network. And even if computer vision has moved from convnets to VITs, um, vision transformers are also susceptible to adversarial examples. Um, so we still, we've made progress. It's better than it used to be, but we still haven't solved it. There's things like that where I still think like there's still threads to pull on. There's still things where we might find one day that these things could be made exponentially better. I don't know how to do it, but I'll probably never shake the suspicion that we could.
The point you noted, I guess, a little bit earlier about, I guess, the way you put it of self play working in a domain where you've got rules was interesting in connection to LLMs, because I think that there's maybe a contrast between the LLMs and specifying or kind of understanding or doing something with the entire world version of this where everything is open, and then LLMs just as limited to language. I guess depending on your view of linguistics, where you might think that, or thinking about language as having a bunch of formal grammatical rules and things like this, and you can kind of do anything within the bounds of those rules, then maybe you view things a little bit differently. And of course, we've seen what LLMs are doing with just language alone. But yeah, the moment you step outside of that, I suppose, and think about like the word world connections and how all of that pans out, it starts to get a little bit more shaky.
Yeah, I mean, well, people are trying to do everything with LLMs right now. It's a Swiss Army knife, or it's maybe it'll be AGI. Like, I don't know. So there's certainly a lot of ferment happening right now. A lot of experimentation. Um, I've seen a lot of things where it feels like trying to fit a square peg into a round hole. But as I said, I've certainly been wrong about things before. I think language models today are able to do things that 5 years ago I never would have expected to see in my lifetime. I think a lot of other people wouldn't have expected to see in their lifetime. And I think precisely because there's been such a huge leap, a lot of people are willing to say, like, the rules have gone out the window. Like, nobody knows what'll work. Let's just try things. So I mean, I think that sort of experimentation is admirable. But I don't want to open my mind so wide that my brain falls out. Um, but yeah, it'll be interesting to look back, I think, in 5 years and see what has worked and what hasn't, and if things do feel like they're stagnant, or if there will be the new paradigm after LLMs that people have moved on to, or I think we will see progress in sort of integrating some of these ideas together. Like, as I said, a lot of when I was doing spectral inference networks, a lot of people were taking ideas from before deep learning and fitting that into a deep learning paradigm. And now we're seeing the same things of taking things from, RL or things like this that were uh, fruitful before LLMs and fitting that into more of an LLM paradigm. So I don't know if sort of a new paradigm will have emerged, or if we'll be in a world where uh, it's all LLMs and diffusion, but just with more bells and whistles that help things work even better. It's kind of anybody's guess. It's the field is wide open.
When it comes to paradigms and methods, one thing I was curious for your opinions on was, of course, we've seen RL kind of coming back, and RLHF that has really done a lot for LLMs. But another thing that I've heard some ML scientists, especially those who really like reinforcement learning, say is thinking about the human brain as like a proof of concept of reinforcement learning working. And maybe connecting back to our earlier conversation on analogies between ML and the human brain and what we seem to be doing, I'm curious if that's an analogy that you have strong inclinations one way or the other about.
Well, I think you probably never want to ask an RL person where the reward comes from. That's question number one. Um, I certainly think the kind of classic work on sort of TD error in basal ganglia is beautiful work, and there's lots of fruitful analogies there. Uh, at a certain point, I guess I just stopped worrying too much about whether you could say the brain works like something or not. Trying to build artificial intelligence is a lot like trying to build artificial flight, and the Wright brothers actually did take a lot of inspiration from birds. Apparently, they would literally run around and hold their arms out and try to imagine what it was like to be a bird, and got them thinking about control surfaces and things like this. Um, and so it was a very fruitful avenue for them, not necessarily to become ornithologists or pore over ornithology papers, though I think they may have done some of that, but kind of get the right kernel of an idea and then take it, abstract it away, and make it work. And again, kind of not look back. And now, if you're designing jet engines, like, who cares if a bird uses a jet engine or not, right? And you look at some neuroscience inspired AI, and some of it might feel like trying to stick feathers on a jet engine. Though again, it can be hard to say until you try it which ones are like the Wright brothers and which ones are sticking feathers on a jet engine. So, but I think I sort of stopped worrying too much about does it work like the brain, and sort of got to a point where I thought, okay, the most fruitful path is just to try it and see if it works, because it's much 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 faster to just iterate and try things than it is to figure out if the brain does a thing. Because fundamentally, maybe this happens if you delve deep enough into any field and you realize nobody really knows anything. But, everything you sort of learn as kind of pop neuroscience, the more you get into it, the more you realize there's no consensus around things. You can always find somebody who will say, well, that's not really how the brain works. And any kind of useful analogy you can draw at the level that would be useful for designing better machine learning or better AI, if you dig too deep, it often kind of falls apart. So it's useful as a source for inspiration, but it's not necessarily something you want to keep yourself up at night worrying, well, does this work like the brain? And when I think somebody argues we should invest in this because it's how the brain works, I'm always sort of tempted to be like, well, is it how the brain works? Really? Like, really know? We don't really know. We know some things roughly, but um, that being said, yeah, it is. But it is interesting how much stuff comes back, and even as much as I try to sort of suppress my desire to make analogies like my brain, like a brain, and I try to sort of not anthropomorphize things, you almost can't help it. So you do see things in kind of currently existing AI, and I think, oh, that does remind me of kind of that thing or this thing, or so it comes up almost involuntarily. But as for why I think reinforcement learning, even outside of RLHF, still has a role to play, I say the most compelling argument for me is less about by analogy to the brain, but it is more about this ability to exceed the data that it's trained on. It's this ability to say it's not just going to match the best thing in the data that it's trained on, but that it can actually kind of discover new behaviors and new patterns that weren't in the sort of thing you would get in super unsupervised or supervised learning, or I guess behavioral cloning, if you want to call it that. So it's this ability to transcend the data, create new data, and sort of bootstrap itself from that data. That I think actually is really the powerful thing about RL, and that I think is true. The brain probably has to do something like that. How much it looks like TD learning or actor critic, I don't know. Um, but I think the brain probably has to do something like that, and I think sort of successful AI will probably have to do something like that.
I was thinking about this diagram you put in a presentation you gave on small language models where you were comparing a bunch of different methods, and one of them was the really interesting probabilistic deterministic infinite automata method that you worked on like way long ago. And I guess that was a method that had some scaling issues, but you were looking at kind of comparing n-gram language models and PDIAs and LLMs and state space models with a question mark, as they kind of covered this range of prediction error versus number of parameters. And I guess PDIAs are like on the very low end of number of parameters. But I'm thinking about one of the questions you posed there, or one of the things you pointed out was there still aren't really any models that cover the entire Pareto front. And I don't know, maybe this is a restatement of the questions I've kind of already been asking you, but I'm wondering if you feel like if you had to think about a model or something that to you could potentially cover the entire Pareto front, what do you think that might look like, or what do you think some ingredients might be?
Yeah, yeah, no, great question. So yeah, the PDIA, the probabilistic deterministic infinite automata, um, was actually my first NeurIPS paper, and so this is from prehistory of language models. This was 2010, and at the time, deep learning was still something just a handful of labs in Canada were doing. Um, and the best language models in the world were n-gram language models. We were just looking at character level language models, and this was also at kind of the height of non-parametric Bayes as being like the cool thing in machine learning at the time. And the idea here was that you can place priors over the parameters of your model that they're basically infinite dimensional objects or infinite parameter objects. So in practice, because you only have a finite amount of data, you would only ever instantiate a finite number of those. But in a mathematical sense, it would be like if you were doing a clustering model, rather than fixing the number of clusters, you would have a potentially infinite number of clusters. And then as data comes in, when you're doing inference or learning, you would assign data points to clusters, and they would have this sort of rich gets richer property. Most data points would go to existing clusters, but every once in a while you'd kind of create a new cluster. And so you could show that a lot of people liked this because you could get around having to do cross-validation. So rather than having a bunch of different clustering models or a bunch of different state space models with different numbers of parameters and fit them all and check the cross-validation loss, you could just do one model and it would find the right number of parameters itself. And a lot of research at the time, there was sort of a pattern in these papers where they'd say, we took an existing model in the machine learning literature, we non-parametricized it, and it does as well as the best parametric model. And this was kind of disappointing to me at the time because I thought, I don't want just a model that does as well as the best parametric model. I want something that does better than any existing model. And, I guess I wasn't the only one thinking this because, just a few years later, deep learning took off and took over the world. And, this was back when speech recognition was being done with hidden Markov models, right? And the best large scale vision models were, things with Fisher vectors and sift features and stuff like this. And, deep learning came along and just stomped all of them and has just taken over everything since. And the idea with the PDIA was, okay, like an n-gram model is just clearly wrong. The idea that the way you share different contexts, the way you aggregate the different information together, you're basically saying, okay, let's look at a one word or one letter context, 2 words, 3 words, 4 words, and basically just build a big table over all of these. And if you don't have any data for the really long contexts, you back off to a shorter context. And I thought, okay, this is just obviously wrong. What if we can learn the correct structure for how to kind of share context together and basically cluster contexts? How can we learn to do clustering of contexts? And use these tools of Bayesian nonparametrics, which were very trendy at the time, to do this. And we were not able to get state of the art performance. We were not as good as the best n-gram models, but we were able to get performance as good as some n-gram models with far fewer parameters. So that kind of became the story of the paper. Uh, was we can train really, really small language models, which is why I feel like sometimes my career has been going in the exact opposite direction of like everybody else, because of course everybody loves large language models now. So when somebody did invite me to give a talk about this last year, I gave it the sort of tongue-in-cheek title of "In Defense of Small Language Models." It's like we're still relevant. Um, but as for what would sort of cover that entire Pareto front, oh, and I should say, a year later, while I was working on trying to scale this stuff up, this blockbuster paper came around on using RNNs for language models, which blew all these n-gram models out of the water. And one of the authors on that was this PhD student in Jeff Hinton's lab named Ilya Sutskever. And it was the first I'd ever heard of the guy, but clearly like he was going on to onto big things. The other author was James Martins, who I now work with quite a lot at DeepMind. Is a fantastic guy, and So there's no hard feelings. Um, but as for what that Pareto front would look like, I do think that, and again, this is the physicist in me loving models with small numbers of parameters, parsimonious models. Even just, coming back to what I was saying about part of what I love about Geomancer is that on small manifolds, you can train it on just a few hundred data points. These models, what I've never seen brought back in the deep learning era, that was something that was nice about Bayesian nonparametrics, was that the models grow to fit the data. You don't add new parameters in unless the data demands it. And so I think a model that would cover that entire Pareto frontier would be something like that, a model that grows with the data. And this is an idea that people have tried. When I went to DeepMind, there was a lot of excitement about an old paper from back in the old days of neural networks. Back in like the 80s or 90s, on like I think it was called like a growing neural gas or something like this. And it was just one of these ideas that nobody was ever really able to make work. And of course, people have tried, Bayesian neural, forget the non-parametric, but just like vanilla Bayesian neural networks is, of course, an idea that people have tried lots, and also has, never really seen mass adoption. Um, but yeah, I think there's still got to be, in terms of ways to unlock it, there's got to be a way to squeeze everything that you can out of every data point without sacrificing the ability to scale. Something that sort of looks like an NP Bayes model with small data that kind of gracefully turns into a giant neural network that you're doing gradient descent on with giant amounts of data. It would probably look something like that. But I think there's also an element of kind of the hardware lottery, as Sarah Hooker puts it here, that on modern GPUs, you just compile your computation graph and it runs super fast on accelerators and things like that. And these kind of models that are kind of growing and branching and splitting don't play nicely with this hardware so much. So we might be. I mean, I hope we're not locked into a world where that can't work. But it does seem like there's a much bigger moat for that kind of work, just because of modern GPUs and other accelerators, the way they're designed.
Yeah, it does seem like there's a doubling down in that regard. Even the new accelerators I'm seeing coming out, it's all like not just the accelerators themselves and what the architects are doing with the components, but everything up the software stack and the compilers too. It's all, let's optimize for transformers because that's where the customer demand and the money is. And so maybe there's a few different bets out there, but I think they're kind of overwhelmed by doubling down on the same thing from what I can see.
And look, I mean, we're still using the Unix operating system or descendants of Unix, 50 years later. Um, the C programming language was designed for like the model of the PDP-10, and all modern CPUs are designed to basically be like really fast C engines. Like these moats can last a long time. So not to be pessimistic about it. At the same time, I do think machine learning has driven probably the biggest disruption to hardware in my lifetime. Is seeing GPUs take off like this. Cards that were designed, I mean, it's the G in GPU cards that were designed for computer graphics, and then accidentally found a use for crypto mining, and now generative AI. It's which in a weird way is kind of bringing them back to graphics again. But so these moats can last for a very long time, but also when they do break, it can be quite dramatic. So it's just a matter of demonstrating that it works.
A thread I wanted to pick up on that was lingering from earlier in our conversation. This was kind of the most clear in the disentangling by subspace diffusion paper. And that kind of plays a main role in this really wonderful blog post you wrote called On Slow Research. And I loved just sort of the illustration of, well, reading the paper that you published before disentangling by subspace diffusion, where you kind of offered this novel definition of disentangling. And that introduces many of the ideas that kind of come into this eventual geomancer algorithm where you're figuring out what can we actually do with this. But it was interesting just to see that story of the problems that were kind of bothering you over time and then how that all eventually comes together given the right inputs. And it was just really cool to see like what all went on behind that. But you also we were kind of talking about this earlier in the context of chasing the big questions. And it felt like to me, based off of the blog post and what you said today, there was something that for some reason really attracted you to this problem. And I think that when it came to things like attractive properties of theories and stuff like this, uh, it seems like there's elements of just mathematical interest and things like that that draw you to certain problems or certain ways of solving problems. But I'm wondering when it comes to what you see as some of the larger questions you've tackled or are trying to tackle throughout your career, how you think about the question of maybe at a deeper level than like this is mathematically cool.
That's a good question. Yeah, some of it, well, like with some of the computational quantum physics stuff, like the FermiNet and that sort of stuff, I think some of it is just having that realization of one, this will work, and two, no one's done it before, and that can be quite intoxicating. Um, but that almost is the opposite of sort of what you said about chasing the big question. That's almost more like a race to be the race to be the first to get the prize. So there's an aspect of that in all research, of course. It's very exciting when you realize that kind of something, or you at least have a promising hunch that you haven't seen anyone else do. You're like, oh, hey, this could work. But as for what attracts me to certain big questions, um, there's an element of beauty. There's an element of the beautiful idea of. I do think part of, for me at least, what really draws me to things is this chance to bridge these seemingly incomparable chasms between fields. Because I have kind of jumped around between fields a lot in my career. I think I've had kind of a slower path up the research ladder than some people, because I have kind of meandered and certainly gone down dead ends in my time, and I've been very fortunate to be able to have a career where I can do that. If you do that too much, and you don't have anything to show for it, you can be just dead in the water. Um, but I think it's the ideas that have attracted me the most in my career. Yeah, like for Geomancer, I mentioned in this essay, you mentioned that the tiny kernel of the idea was like almost 20 years ago. And again, maybe I was a bit. I don't know if Jeff Hinton's the best guy to take career advice from, but you hear him talk about capsules and saying, I worked on capsules for 17 years, and also in some sense, capsules maybe haven't had the impact that he had hoped. So maybe working on one idea for 17 years isn't the best strategy always, but the kind of people who are going to do it are going to do it. They're people who are obsessed, and I'm one of these people. But the original kernel for this idea was studying differential geometry in my by day, and going to see Douglas Hofstadter lectures by night, and saying that, oh, the math that I'm learning for general relativity could say something about analogical reasoning and cognitive science. It's this bridge between ideas that I think is probably what I find the most attractive in my own career. Different people are motivated by different things, but I think that's it for me. It's drawing these unseen connections, almost, and not just a connection for a connection's sake, but saying, oh, this can really unlock something that people have really been puzzling over, or I think in some ways even better, things that people didn't even know they should be puzzling over. You know, it's for me, if you can come find something where it's one thing to answer a question, but if you can discover something where you make people ask a question they didn't even know to ask in the first place, that that is, I think, that's the deepest thing to me. That's the most exciting thing to me.
And I guess in this essay, also, one thing you kind of described was the feeling that I think we've kind of already gone over that you're not all the way there yet with this method and this line of thought. I think you described it as a bridge going halfway to a destination that is a beautiful bridge, but not quite there, but also like the culmination of many years of thought. And I'm wondering how you think about maybe two questions. One is if you have thoughts on what the rest of the bridge might look like, and two, maybe if it remains a halfway bridge, how that would make you feel.
Uh, well, I do have some ideas, but you know, it's probably best not to speculate too much on unpublished things on podcast. Um, but as for you know, would I be happy if it's left half finished? Well, obviously, I'd be a little disappointed. But I don't know. I mean, to mix metaphors, it's a bit like you know, you plant an acorn and you hope it grows into an oak tree. Um, Whether it grows into an oak tree or not, you know, sometimes it depends a lot on where you plant it. If it's there's a lot of sun and light and water, it'll grow. If it's you know in an already crowded forest, it might not. So yeah, I think nothing's ever really finished. So I think it would be hubristic to say like, you know, yes, we will solve all problems. We will finish this bridge. But I certainly want to see it taken further. You know, I'd love to see it taken further.
Maybe expanding that into a broad question, which might be a good place to close on. I'm thinking about, I look at your papers and your career and how you think about your work, and it feels very aspirational to me personally. I feel like you've worked on some very, very interesting problems that are impactful in ways that, at the very least, are kind of attractive to me personally. And you seem to have a really grounded sense of the stuff you're doing, how it plays a role in the broader community, and what kind of attracts you. And you have like a really keen sense of what that is, and you're just able to kind of go after it. And I suppose I feel like I, and maybe a lot of people listening to this too, are thinking about balancing the how do I go after the things I want to go after or just feel intrinsically interesting with the practical demands of everybody is working on the same thing right now, and this is where the money is and all of that. Of course, everybody has kind of different paths through this, and you have a very particular path of your own, but I'm curious how you think about the balancing of those two things, and maybe how you feel like you found it, or how you'd recommend other people trying to work that out think about this.
Yeah, I say, well, first of all, I'd say I don't know if this is reassuring or disappointing, but I'll say that I struggle with all of those things that, you know, you struggle with too. You know, every day is a new day. After every paper, you have to ask, okay, what do I do next? What's the kind of next stage of my career? And, you know, I don't know that better than anybody else does. So I have to kind of constantly calibrate that as well, just like anybody else does. Um, in some ways, I think I might be like I've definitely made decisions in my career just to obsessively pursue one thing that might not pay off. And, you know, it hasn't always paid off. I mean, it hasn't always paid off. You know, sometimes it has set me back or there have been opportunity costs, and it's meant that it's taken me longer to reach a certain career stage than it might otherwise have. But I'd say I entered that kind of with eyes open, and I knew that I was taking that risk. Um, in my PhD, I struggled quite a lot with this because I really a PhD can be such a difficult time for people, um, and I really worried that I had kind of missed out, you know, missed the opportunity to have the career that I wanted to, and that you know I was seeing other people advance faster. You know, at least to me, it seemed like they were advancing faster than I was, and I seemed like I was going in a direction that I wasn't happy with. And even just a few years later, I sort of looked back and was like, what was I so worried about? Um, I ended up having far more second opportunities than I expected to. And so I don't know if I could give some advice just to myself, you know, a little over a decade ago. I would say you'll get more second opportunities than you expect. Some of it was luck, some of it was just the right timing. Um, you know, I was worried that I was applying to DeepMind too late, but you know, I was applying right when they were hiring a lot of people. Um, but you know, if certain areas have become more mature, there's always something somewhere that's growing like crazy, and there are always opportunities. Um, it. there might be some, I don't know, there might be years of wandering in the desert, but it's you just, yeah, I'd say you'll have more second opportunities than you expect, but it also does take a lot of chutzpah and a lot of patience and, you know, a lot of frustration along the way. So but it's worth it. But it's
Yeah,
worth it.
I think, yeah, I mean, at least for me looking at your work, it seems like it was very much worth it.
I think some of it was feeling that I had a second opportunity in my career. I didn't want to waste it. You know, I didn't want to say, you know, I've been given this opportunity um, to follow through on a lot of the crazy ideas that I've had, and to think, well, okay, is this really like where the field is right now? Is this really the way to maximize my impact? Is this what the trendy thing is to work on? I sort of said, you know, no, look, you get one life. I got a chance to swing for the fences, and as much as possible, I have.
I really appreciate that. And I think that's probably a good note to end on. So I'm a big fan of your work. I really appreciate that you took the time to talk to me today. Thank you for this.
Well, thank you for having me. It's been a pleasure.
Thank you, as always, for listening, and thank you to my guest, David Pfau. The best thing you can do if you like this is to share it with other people who might as well. Thanks, and I'll see you in the next episode.